Hello and welcome to Honors Function. In this lecture and the next, we're going to be looking at a local behavior of polynomial functions. More precisely, we're going to be looking at the behavior of a graph of a polynomial function around its x-intercepts. Let's begin with a definition. So this is a definition we have seen before. If you have x naught a solution to the equation f of x equal to 0, okay, that means f of x naught is equal to 0, then x naught is called a 0 or a root, okay? And graphically, you would say that x naught 0 is an x-intercept of the graph. So we have seen that before. This is just a reminder. I will interchangeably call it a 0 or a root. And if I think about the graph, I may call it an x-intercept, okay? It's all almost the same thing here. Let's begin with the first example. Here is the first polynomial function I want to look at. It's a product of 4 factors, 3 of them being variable factor and 1 of them is a constant, okay? If you were to study, for example, the inequality 1/2 times 3x minus 4 times x plus 1 times 2x plus 5. Suppose you wanted to study greater than or equal to 0. In your sign chart, you would have to write all the factors 3x minus 4, x plus 1, and 2x plus 5, right? Recall the previous lecture. I don't need to write 1/2 because it's positive. Here would be my line of x's, right? And in the end, I would have the expression right here, right? Suppose I'm only going to look at one factor. For example, I'm going to look at this one right here. I would have a negative 1 right there. Everything would be negative before and positive after in this row. And I would have a 0 right here, okay? So I would say that at negative 1, there is a sign change. This factor changes its sign at negative 1. Now, of course, if this factor is squared, it's not in this case, okay? But if it were squared, you wouldn't have a sign change, all right? So let's think now about the graph of these polynomial function. Let me erase that. Okay, so if you were to graph this polynomial function, or rather sketch it quickly, what would you do? You need the leading term, right? So the leading term is 1/2 times 3x times x times 2x, right? So the 2 and the 2 would cancel and we would have 3x cubed. So it behaves like a line going up, right? Odd degree, positive slope. Okay, so here is how I'm gonna sketch the graph. 1, 2, 3, negative 1, negative 2, negative 3. Let me plot my x-intercept. I have negative 1 right here. I have 4/3, 1 and 1/3, and I have negative 2.5 right here. And it behaves like a line going up, right? So my graph is going to be coming from here and it's going to go somewhere here. Now, I would change the sign around negative 5/2. There is a sign change around negative 5/2, a sign change around negative 1, and a sign change around 4/3. Graphically, what does it mean that there is a sign change? That means the graph crosses the x-axis. You see, it was negative before, and then it's positive after. What is it? The output of the function, right? So a sign change means you cross the axis. And then you cross the axis again at negative 1, and you would cross the axis again at 4/3. And so we have sketched the graph quickly of this function by plotting the behavior around each 0. And in this case, the graph crosses the axis. Why? Because if you think of a sign chart, when you write your rows, you would have some pluses and minuses before and after each of the zeros here in each row, okay? Let's look at the second example. Okay, so here is another polynomial function, and the degree is still 3. Let me get the leading term here again. I have 2 times x squared times x. So it is 2x cubed. So here again, it's going to behave like a line going up. Okay, now let me get the behavior around this quadratic expression here. Let me see the 0 here. Why did I not factor that? Let me look at it. X squared plus 2x plus 2 equal to 0. So let's complete the square. X plus 1 squared minus 1 plus 2, that's plus 1. And I understand why I didn't plot it, because this doesn't have its equal -1, right? This doesn't have any real zeros, okay? The zeros are complex. This is never equal to 0, right? So if it's never equal to 0, it does not generate any x-intercept. There is no x-intercept coming from this one. No x-intercept. Right here, okay? Why? Because you don't have any real 0. An x-intercept has to be real. It's a point, really, but the x-coordinate of the point has to be real. Why? Because here is the real axis. This is a real line. It's not the complex line, right? This is a real line. So how would you plot this function? Well, there's only 1, 0 at 3. So let's put 3 right here. And then the function goes from here to there. So I'm not sure exactly what's going to happen. I know it's not a line, right? It's a degree 3. So maybe it's going to be something like this. Maybe it's going to be something like this. I don't know. Maybe it will be like that. I'm not sure, but I know there's only one place where it crosses the x-axis, and this is at 3. Why? Because there is a sign change at 3. Okay? So this is for the second graph. Let's look now at the third kind of equation. Here we go. We got again a degree 3 polynomial. The leading term here again is an x cubed, so it behaves like a line going up. Let me plot it. Now let's think about it 1 second. We have 2, 0. One is at 0 and the other one is at -2. But now let's think of a sign chart. Suppose you wanted to solve the inequality x times x plus 2 squared positive or equal to 0. Okay? How would you solve this inequality? Well, in the sign chart, here's the line of x's. In the sign chart, you wouldn't need to put this factor because it's always positive or equal to 0. I would write -2 because, you know, I mean, if you had an equality here, right? But there wouldn't be, look, if I were to do this, there wouldn't be any sign change around -2. It's positive before and it's positive after. There is no sign change here, right? There is a sign change though around 0, right? Negative before and positive after. Oops, positive. There is a sign change around 0 right here, but not around -2. So what does it mean graphically? It means that the graph doesn't cross the x-axis. I repeat, the graph doesn't cross the x-axis. It does touch the x-axis because you do have a 0 right here. Therefore, what you have right here, you just bounce on the axis like that, and then you cross at 0 because there is a sign change. Okay, so we've spotted two types of behavior at a 0, at a root, at the next intercept. You can either cross it or bounce on the axis, and that depends of the power here of the factor that you associate with the root. I repeat, it's a function of the power of the factor that you associate with the root here. Okay? Well, we have a very specific terminology to address this power right here. Let's look at the next definition. So given a polynomial function, if you can factor x minus a to a power, let's say r, if you can factor x minus a to the power of r and then times, well, times whatever else you multiply by, right? But assume that you cannot factor more than x minus a to the power of r, right? So this wouldn't be possible. If you cannot do that, if you can't do that, right, if this is not possible, the maximum power is x minus a to the power of r. We say that a is a root of multiplicity r. A is a root of multiplicity r. That means it's a root r times. It's just a root several times, okay? Because you can write it as, so forget this, you can write it as x minus a times x minus a times x minus a, and all of that r times, right? Times p of x. So it's a root once, twice, thrice, r times. It's a root r times, basically, okay? Root of multiplicity r. Let's go over the first example together. Here we go. Find the roots of the polynomial below and determine their multiplicity. So I'm going to do number 1 and you're going to do number 2. So this is super easy. The polynomial is already factored. Here I'll answer as in a table. Roots, and I'm going to write the multiplicities right here. Multiplicity. So what do we have? We have 0, right? How many times is it a root? Twice. Why? Because the factor is squared. Then we have negative 2. How many times is it a root? Well, only once, multiplicity 1, okay? Then we have 3/2 right here, okay? 3/2. How many times is it a root? Well, 3 times, multiplicity 3. And then we have 5/3. How many times is it a root? Twice, okay? A root twice. So graphically, we know now what happens graphically if you think of a sign chart. There is no sign change right here, no sign change around 0. There is a sign, no sign change. There is a sign change around, negative 2. There is a sign change around 3/2, multiplicity 3, right? So it will change its sign. And there is no sign change around 5/3. So what does it mean, this sign change or no sign change? It means here you would bounce across the x-axis. If you don't have a sign change, you bounce, you don't bounce across, you bounce on the x-axis. Here you cross the x-axis, here you cross the x-axis, and in this route, for this route, you would bounce on the x-axis, okay? All right, please do number 2, and I'm gonna do number 4. Well, for number 4, it's not written in a factor form, therefore I have to factor it, right? Okay, so let's factor. First thing I will do, I'll take an x squared out, so it's x squared times x5 minus 4x cubed plus 8x2 minus 32. Okay, now what do I do here? I'm looking at the coefficient, and I'm thinking maybe a grouping, right? So I would say x squared times, so let me take x cubed out of that, x cubed times x squared minus 4, I can easily factor this, plus I'll take an 8 out of that, yeah, that's gonna work very nicely, and you got your x squared minus 4. So now what? Now let's factor x squared minus 4, and we have x squared times, all right, here I'm gonna have x squared minus 4, right? But times what? Times x cubed plus 8, right? If you distribute right here, you would get back to the previous line. Okay, got it. All right, and now we need to finish it. So x squared times, this is a sum of cube. I do expect you to know the formula right now, okay? It's x plus 2 times x squared minus 2x plus 4. And here we have an x plus 2 times an x minus 2. Okay, so what do we have? We have, here I'll write it in a different color. We have x squared times, how many x plus 2? 2. So x plus 2 squared times this, if I haven't made a mistake, this doesn't have any real solution, right? They're all complex. Times x squared minus 2x plus 4, right here. And then finally times x minus 2. That's it. Okay, times x minus 2. So now let's answer the question, right? So the question was, what are the zeros and their multiplicities? So here, let's write roots and multiplicity right here. So what are the roots? We have 0, we have negative 2, we have, well, these are complex roots, and we have 2, only 3 real roots, and their multiplicity, 0 is 2, negative 2 is 2, and at 2 I have 1, okay? That's it. This will allow us to solve inequality much faster than with a sign chart. Let's look at the next example, example number 5. So in this example, we have to solve this inequality now. This polynomial is the same as above, therefore this inequality is equivalent to x squared times x plus 2 squared times x minus 2 times x squared minus 2x plus 4. Now, I am not gonna do a sign chart for that. I'm gonna solve it graphically. It's gonna be much faster than with a sign chart. Check it out. 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. What are my zeros? 0, negative 2, and 2 right here. The graph, the leading term is x7, so the graph behaves like a line going up, right? So I know it's gonna start here and I know it's gonna end here. All right, let's sketch the graph quickly. At negative 2, it's a root of multiplicity 2, therefore you bounce on the axis, you bounce. Then what's going on at 0? I don't know how low it goes right here, right? But I know I'm going to have to get back. Here, let me redo it. I know I'm going to have to rise back to 0, and I bounce again, so I cannot go too low, right? I need to bounce again because it's another root of multiplicity 2. And then at 2, I cross right here. So solving this inequality now is super easy. I see it graphically. I'm going to fetch this branch and also these 2 points. Therefore, the solutions are negative 2 infinity, right? This is this right here, or it's also going to be 0 at negative 2 and at 0. That's it, right? Pretty fast like that. So please, you do example number 2, 3, 6, and 7. Please, for 6 and 7, do not draw a sign chart. Do a graphical reasoning, please. Do a graphical reasoning. Okay. Now, to finish this lecture, I'm going to be looking at another type of behavior around the 0. For that, let's look at 2 examples that I have treated in my notes. So, look at this function, for example, right here. Okay, f of x equals x minus 1 squared times x plus 2 to the power of 4. Now, both roots have an even order, right? 2 and 4. Therefore, there is no sign change at 1 and there is no sign change at negative 2. The graph is going to bounce on the axis at 1 and it's going to bounce on the axis at negative 2. Here we go. Look at, you can see how it bounces. But it doesn't bounce in the same way, and this is what we need to understand. See, at 1, it bounces much faster than at negative 2. At negative 2, it's flatter. We're going to explain this, but before we explain it, let me look also at the other function right here next to it. This one, x minus 1, that's power 1, right? Times x plus 2 cubed. So what's going on here? They both have odd powers, right? Odd powers. Therefore, they will be both crossing the axis. There is a sign change. But you see how it crosses? It crosses in 2 different ways. Much faster at 1, okay? And it crosses in a flatter way around negative 2. What's going on here? Well, let me show you something. Okay, let's take a real number x between 0 and 1. X is in between 0 and 1. Let me look at this part right here. If I multiply both sides of this inequality by x, x is positive, okay? X is positive. So I can multiply both sides by x, and I have x squared is smaller than x. Let me multiply by x again. If I multiply by x, I would have that x cubed is smaller than x squared, and here we said that x squared was smaller than x, which is smaller than 1. Okay, let's multiply by x again, this one. So we would have that x4 is smaller than x cubed, which is smaller than x squared, smaller than x, smaller than 1. So you see, if you multiply by x, you're going to get a power that is lower than the previous power. Graphically, what does it mean graphically? So look, let me take 1 right here. Here we go. So this is x equals 1, y equals 1 right here. And let's take the first graph is going to be y equals x right here. Okay, this is y equals x. Now, what is y equals x squared? Well, I said that x squared right here, the first inequality was x squared is smaller than x. And we know what it looks like. It's a parabola, right? Y equals x squared would be, for example, right here, right? That would be, for example, y equals x squared. Where would be y equals x cubed? Well, it's got to be lower than x squared. So y equals x cubed would be, for example, right here. Y equals x cubed. So let's do it one more time. Where would be y equals x to the 4th? It would be even lower, right here. Y equals x to the 4th right here. And you can see that for a given value of x, what I wrote here is right there. You can see it right here, right? This is x. This is x squared, which is lower than x. This right here is x cubed, and this is x4. So when you increase the power, you flatten the graph. You flatten the graph if you increase the power. Okay, so this is a description of what happened around 0, but of course if you have like x minus a to the power of 4, you would be doing the same thing, except that it's not at 0, it would be at a. All right, you would flatten the graph. Let's go over the last series of examples. So I'm gonna let you do 8 and 10, and I'm gonna do number 9, okay? You have to determine the equation of the following polynomial. Don't expand it. We're gonna keep it in the factored form. You assume that the polynomial doesn't have any complex root and that all the powers are as small as possible, okay? So let's see. I have here a 0, it's -1. I have a 0 at -1, right? So let's write 0. I have a 0 at -1. And I have another 0 at 2. And I have a 0 at 2. So what do I expect in terms of factor? I expect x plus 1 to be a factor. And I expect x minus 2 to be a factor. Okay, that's the first thing. Now, what's going on at -1? It bounces. So I'm expecting the multiplicity to be even. And it also bounces at 2. So I'm expecting again the multiplicity to be even. So it could be 2, 4, 6, 2, 4, 6. Now, the powers are as small as possible. And here, it bounces in a much quicker way than here. Here it's flatter. Therefore, that's got to be a power 2. And that's got to be a power 4. Right? These are the two smallest even powers, 2 and 4. So the equation of this function would be x plus 1 squared times x minus 2 to the power of 4, okay? So that will describe the zeros, but then, I don't know, I can multiply this by a constant, right? I don't change the behavior around the 0, I will change the shape of the graph. So how do I find the constant? I need a piece of information now. It looks like it's 16 at 0, but actually there is a point that I marked in a much clearer way. At 1 it's 4, so f of 1 is equal to 4. So what is f of 1 now? F of 1 is k times 1 plus 1, 2, 2 squared 4, times 1 minus 2, -1 to the power of 4, 1. So this is just k times 4, and this is supposed to be 4, right? And so k is 1. So here we go. My polynomial function is just this one right here, okay? So please finish all of the other example. Thank you for watching.